Imagine getting to London in 3 hours.
That's the promise behind this jet here, the Boom Overture.
Supersonic travel could be especially important for industries involved in medical transportation and disaster relief.
This aircraft isn't just fast, it's doing something experts quietly agreed should never be possible. For decades, engineers believed there was a hard ceiling in the sky, a point where physics itself pushes back so violently that no machine could cross it and survive. Yet somehow, a new generation of aircraft is creeping past that invisible line, not with rockets, not with disposable tech, but with something far more unsettling, a reusable jet. The kind that takes off from a runway, lands like any other plane, and then does it all over again. And at the center of this breakthrough is a company most people have never heard of, Hermeus. What they're building doesn't just promise faster travel, it challenges everything we thought we understood about speed, heat, and the limits of engineering. Because if this works, it doesn't just change aviation, it changes time itself. But to understand why this is such a big deal, you have to go back to the moment the world stopped trying.
For a long time, humanity believed it had already reached the edge of what was possible in the sky. The benchmark was set by legends, machines so advanced they almost felt like they came from the future. The SR-71 Blackbird dominated the skies at over 3 times the speed of sound, a black titanium-built aircraft that could outrun missiles and survive temperatures that would destroy ordinary jets. On the civilian side, the Concorde proved that passengers would pay for speed, slicing transatlantic flights in half. But both came with a cost. The Blackbird required extreme maintenance and specialized fuel just to function, while Concorde burned through money almost as fast as it burned fuel. Eventually, both programs ended, not because they failed technically, but because they couldn't scale. And slowly, the industry shifted. Instead of going faster, planes became slower, more efficient, more economical. Speed stopped being the goal. And without anyone officially declaring it, the world accepted a quiet conclusion. This was as far as aviation would go. But not everyone agreed.
While commercial aviation slowed down, something else was accelerating in the background, and almost no one outside defense circles was paying attention. Countries like China and Russia began developing hypersonic weapons capable of traveling at speeds far beyond anything used in traditional warfare. These weren't just faster missiles. They could maneuver mid-flight, evade detection, and strike before defenses even had time to react. Systems like China's DF-17 and Russia's Avangard introduced a new kind of threat, one that existing defense systems weren't built to handle. And suddenly, the problem wasn't just about speed anymore. It was about response time, survivability, and control. Because missiles, no matter how advanced, are single-use. They launch once and they're gone. What military planners really wanted was something different, something reusable. An aircraft that could take off, fly at hypersonic speeds, complete a mission, and return safely, again and again. That's the gap Hermeus set out to fill. But chasing that goal meant confronting a problem that had already stopped nearly everyone else.
Most people assume the challenge of hypersonic flight is about speed. It's not. The real enemy is heat. And not just a little heat, but temperature is so extreme, they begin to break down the very structure of the aircraft. At Mach 5, the air itself becomes the problem. As it slams into the surface of the plane, it compresses so violently that it heats up before even making contact. This process, known as aerodynamic heating, can push temperatures beyond 1,000 degrees Fahrenheit. At that point, aluminum melts, titanium weakens, seals fail, electronics shut down. And this isn't a brief moment like a spacecraft re-entering the atmosphere. A hypersonic aircraft has to survive this environment continuously, holding those speeds for extended periods. That's why so many projects in the past either failed, melted, or were quietly abandoned. The laws of physics weren't being broken, but they were pushing back hard enough to make progress feel impossible. So the question became, how do you build something that doesn't just survive that heat, but operates inside it?
The answer doesn't lie in the shape of the aircraft. It lies deep inside the engine, specifically one of the most unusual propulsion systems ever attempted. Hermias calls it chimera, and it works in a way that almost sounds contradictory. At low speeds, it behaves like a traditional jet engine, using turbines to compress air and generate thrust. But as speed increases, those same turbines become a limitation. So the engine transitions, shifting airflow away from the turbine and into a completely different system known as a ramjet, which has no moving parts and relies purely on the aircraft's speed to compress incoming air. The idea of combining both systems into one engine isn't entirely new, but making the transition between them work, that's where everything falls apart. Engineers call this moment the Valley of Death, where even a slight failure can cause total loss of thrust. Too early, and the aircraft slows catastrophically. Too late, and the engine tears itself apart. For a brief moment, everything has to work perfectly. And somehow, after months of testing, they made it through. While commercial aviation slowed down, something else was accelerating in the background, and almost no one outside defense circles was paying attention. Countries like China and Russia began developing hypersonic weapons capable of traveling at speeds far beyond anything used in traditional warfare. These weren't just faster missiles. They could maneuver mid-flight, evade detection, and strike before defenses even had time to react. Systems like China's DF-17 and Russia's Avangard introduced a new kind of threat, one that existing defense systems weren't built to handle. And suddenly, the problem wasn't just about speed anymore. It was about response time, survivability, and control. Because missiles, no matter how advanced, are single-use. They launch once and they're gone. What military planners really wanted was something different, something reusable. An aircraft that could take off, fly at hypersonic speeds, complete a mission, and return safely, again and again. That's the gap Hermias set out to fill. But chasing that goal meant confronting a problem that had already stopped nearly everyone else.
If that moment succeeds, the impact goes far beyond engineering. It reshapes how the world moves, responds, and connects. On the military side, it enables aircraft that can reach targets across the globe in under an hour, complete missions, and return before defenses can react. Not as disposable weapons, but as reusable platforms that adapt and evolve. On the civilian side, it unlocks something people have dreamed about for decades: true high-speed global travel. A future where crossing the Atlantic takes less time than watching a movie. Projects like Halcyon aim to make that a reality, turning what used to be an all-day journey into something closer to a commute. Of course, challenges remain. Regulations still limit supersonic travel over land, and competitors like Boom Supersonic and Stratolaunch are racing towards similar goals, while others like reaction engines have already stumbled. But the difference now is momentum. For the first time in decades, hypersonic flight isn't just theory, it's happening. And if it continues, the sky won't just look different, it will mean something completely new.